we're going to talk about science today. I see a few people are excited about it. And we're going to talk about our inner energy. What that kind of energy, we're going to talk about infrared energy. So we're going to talk about the James Webb Space Telescope. And this telescope, the main thing about telescope is that we are good in looking into the past. Something that should have left behind with another relationship and things like that. But no, let's talk about it. First thing is that for me it's a pretty important thing to say that this is a collaboration with thousands of people around the world, and that's the main thing, especially in this day era, especially Canada, Europe, and thank you, appreciate it. There it goes. Now, talking about size again. But especially, I'm pretty happy about this telescope because it's been a collaboration around the world, and this is really important in this day and era. First, let's start with the liftoff, right? This happened in December, literally in Christmas Day 2021, and we're gonna see a little video about it, and then I'm gonna go through it after that.
Top, à 0 moins 1 minute.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 30 seconds and count. Standing by for terminal count.
À tous de dédélo, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
But the main thing is like everything looks so nice after liftoff and everything, but that's not the hard part. The hard part is like this telescope lasted over 20 years to be done after $10 billion in the making. And why we spend that much money and that much time in a telescope? Well, the main thing here is the infrared light. As maybe some of you know, we have a spectroscopy of light. So light goes from gamma ray to all the way to visible light and radio. So one thing that is really important about this telescope, because most people know about Hubble, and it's one of the best. We have Spitzer too, it was an infrared telescope too. But if you can see in this graphic, you can see the visible light, that's the only thing we can see. So if you can see the spectrum of light is huge, and we're missing most of it. Another thing is like even Hubble, it was mostly a visible light telescope, and although it was great and we discovered so many things, look, all the James Webb Space Telescope is gonna see in the infrared that you can span that spectrum all the way, and only a little bit at the end you have a Spitzer, that was the next telescope. So one thing you have to understand here is like the broad spectrum of light that we're missing. And the importance of the infrared light is that when we're trying to see things that happened in the past, that light that is going, from the real far galaxies at the beginning of the universe, to us, that light stretch. So from the gamma ray, all that really high energy radiation goes all the way stretching into infrared. So light that's being out there for billions of years, by the time that gets to us, it's almost invisible. So we need a telescope like this to look into it. So one thing I can show you here, to prove to you how little that we see, you can see here my friend, I don't know, you can put a name Bob, holding a bag. Bob is hiding something under that. And with infrared, you can see literally right behind that. And as you guys know, the galaxy is really, really empty, but we have a lot of gas and dust out there. So for most of the high energy wavelength, it's so hard to go through those. So infrared, or all of these long wavelengths, they go just through that dust really easy. So we can see way, way farther. And now, of course, this is an infrared telescope. So infrared light is the light that we all emit. Anything that have temperature, like you, I told you we're gonna talk about inner energy. So everything that have movement energy at all have infrared energy. So we have an infrared telescope. We need to put it far away from the sun, the planets, and everything that can shine light into it, or energy in this case. So we put it in L2, that's Lagrange 2. That's a point in space that, I don't know if you guys have heard about three-body problems. There's like a new series out there. Well, that's a real issue. When you have more than two bodies orbiting each other, you add another body, it's really hard to keep that orbit stable. But there was this beautiful guy, Lagrange, and he located like a few points around our solar system that are called Lagrange. And in L2, Lagrange 2, that point exactly is where we put the telescope. So it's far away enough, and we add certain beautiful things to that telescope too, so it will be safe from that radiation. Let me see if you can see the video. So this is how it's gonna be orbiting around our Earth. That way, you can see that the telescope has some shields. Those shields are to protect it from all the radiation that comes from the sun, the earth, the moon, and all that. And so you guys have some perspective. This is the kind of a scale of the planet and the moon, the distance. So that telescope is 1 million miles away from the Earth. So it's 4 times this distance. So you guys can have a better idea how far it is. And now we go with the main thing. We didn't have this technology at all. This didn't exist. So when people say like, wow, over 20 years, almost 30 years, and $10 billion, why, how you guys did this? This telescope is so big that they need to fold it into the point of that rocket that you saw at the beginning, so we could send it out. So that takes a lot of time, effort, and after you create the most powerful telescope in the universe, you have to say like, oh well, where are we gonna put it now? We don't know how to send it up there. So this is what we did. And after that liftoff, and after over 20 years, that was not the hard part of it. This was the hard part. Everything in the telescope have to work properly. Just so you guys have an idea, there is some points of danger in every mission in space. And to give an example, landing in the moon, they have like 90-something points of, things that would go wrong. This telescope, after being out there in space, already still have 344 things that could go wrong. Wow. Especially since the telescope have to unfold when it was when it detached from the rocket, it has to unfold the solar panel, so it will have energy to get to the point where it needs to be. And then by the time it was traveling to the Lagrange point, it has to start folding out. The main thing with this is that a telescope that is in infrared and needs to be protected from the sunlight or any kind of energy, so the images are actual images from us and not something that is bothering the actual data. You have to protect it, and this telescope has 5 layers, 5 shields to protect it from it, and all of those shields have to release an opening space. And if you guys know, space or things, any type of matter, if it's too cold or too hot, it gets damaged. So you pretty much have to stretch in space something that is like a really, really tiny thin foil to protect the telescope. And out there in space, there's 2.7 Kelvin degrees. And if the sun is hitting it, in that side, it could get up to 200, 250 degrees Fahrenheit. So from a point that could be really, really melting to a point that could be almost absolute zero, and that have to work. Not just that, all these panels in there is 18, like the main mirror is 18 different glasses. All of those 18 glasses, they were smart enough to make it out of beryllium. Beryllium is one of the first elements in the periodic table. You have only 4 protons compared with iron, but it's stronger than iron, but it's flexible. So it was like my dad. He looks nice in the outside, but he was a cheetah. So one thing that is pretty cool in this is that you can see that it's gold. So they just put a little bit of gold painting that is only like 100 nanometers. So that's like the size of a hair. So that's really, really thin. But gold is pretty good at absorbing light. So that was one of the reasons. So you can see that the main telescope have like the main mirror that is that big one, have the secondary mirror that is that point in there where all the light gets in there and then reflects to the second mirror, and then that goes back into the telescope so we can process the image. One thing that for me is really, really amazing is that even though after all of this happens, all of those mirrors have to be put in place to work as one huge mirror. So you have one huge telescope. And of course, I told you size matter, huh? So yeah, you can see here how telescopes work is if you receive more light, like if it's raining, you have a small bucket, you will get less water. If you have a bigger bucket, you get more. Light works the same way. So Hubble was great, but look at the size. It was almost like 8 feet. This is 21 feet in size. Now, what is the main difference between visible light and light that we cannot see in simple light? This was one of the most beautiful pictures Hubble ever took. This is the deep field, a Hubble deep field image. In this image, just so you guys have an idea, this took like a few days, like almost 2 weeks, to take this picture. This took a couple hours with James Webb.
Wow.
You can see all those red dots. Everything in this image is a galaxy. And just to blow your mind, what we're looking here is like if you get a grain of sand and put it up and look at it, that's all this space that we're looking here. So it's nothing in space. So yeah, we believe in aliens. Now, one thing that I love about this, and people sometimes don't realize, you can see the bend of space because of the gravity of all these galaxy clusters, and you can see how light bends around. So that's even another proof that we cannot see from here. Even telescopes from here cannot see this, that you can prove Einstein was right too. The bending of space, and you have it in an actual picture here. This is, for me, this is crazy. And you can compare the Spitzer, that was an infrared telescope, between Webb. It is, no doubt it was a good investment. And the difference about all of this is you can see the visible light, but you would see, you see a little near infrared. Look, everything that just turned down there. And then go mid-infrared, you can see, oh my God, there's even more. There's more gas, there's more stuff around. For example, this was one of the farthest galaxies Hubble looked into it. This galaxy is around 13.1 billion years away. So this is one of the main galaxies that we know of so far, but that was not the only one. We have a second one, and this one is to believe 13.5 billion years. So that means this is 400,000 years after the Big Bang. So we're looking at the beginning of the universe already. This was not James Webb. This was from different types of telescope from Earth. This picture was taken in Tokyo. But James Webb will look into it and make sure that what we're seeing is what we believe. And another cool thing, real quick, that James Webb can do is that when light goes through the planets, if we're looking to an exoplanet, we can see through the atmosphere what type of elements are in that atmosphere. That way we can see if like there's some elements that can only be in the atmosphere because something that is alive created, right? Maybe we can locate like, maybe there's life in that planet. And the way to do it is because stars, usually the light that the stars send is a higher energy light, and planets, because they're infrared, because they just reflect the energy in them, we can see them way better than, because lights, like the star in here, if you look during the day, you cannot see anything behind. So with the infrared telescope, you can do that. And to me, one of the most crazy things is things that you discover when you actually look. It's like when you are blind and suddenly they have surgery in your eyes. So let's just go through the main pictures. Deep field, crazy. You can see here that even in the left one that looks so beautiful, you can see with a different kind of infrared, you can see that there is not only one star, it's two stars in the middle. This is another nebula. This is once again the gravitational field. Beautiful. You can see two galaxies colliding. Spin well. Yes. Yeah, on February, the telescope was already there, so around, well, it took a little bit over a month to unfold and be in place and etc. And then the first image release was in July 11. So after the first week, they already have a bunch of pictures. They just have to process them.
Where is the telescope height-wise? Out of the galaxy?
Where's the what?
How solar system?
Oh, it's the telescope is like 4 times the distance from the Earth. It's between Earth and other planets, so it's 1,000,000 miles away.
How as far as Mars?
Yeah, it's 1,000,000 miles away.
Not as far as Mars.
Oh no. I'm sorry, I didn't understand. Yeah, not as far as Mars, no.
How long does a transmission take to get us a picture like you're showing us?
Not a lot, because it is, well, universe is really far, but to give you an example that I can tell you, it takes 1.3 seconds to send information from the moon. So if it's 4 times that, you can see that it's maybe 5-6 seconds. Oh, I'm sorry. Yeah, they said how long it would take the information to get to us from the telescope.
I have 2 questions. First, were you at the liftoff?
Oh no, I wish. It wasn't even in the States.
And also, do you know what the control language for the scientific equipment and who wrote it?
No, I don't know. You know? You know the answer?
I wrote that.
Oh, you did? Nice. When are you gonna present? Well, the question was, what was the language they wrote the code and all?
It was a JavaScript engine that controls all the internal equipment.
Can you repeat that for everybody?
It's JavaScript, which scares
What's
anyone that's
JavaScript?
ever had a crashing web browser. That's what I wrote, and that's what controls all the equipment and controls stuff in space.
Nice. Back there? Oh, that's really nice.
That's a big question.
You need to present. We have to get this guy. Back there.
Can you explain redshift, and did they know about it prior to the deployment of the Webb, or did they find it after?
Yeah, we know redshift since 19.
repeat the
Oh,
question.
the question, sorry. Question is like if we knew about redshift before the telescope, and even Hubble, I believe he said too. And we did. We knew about redshift in 1929 when Edwin Hubble discovered like there is more galaxies out there. So he realized that for some reason, galaxies or stars that are moving away from us, their light that is getting to us is turning red. And galaxies or things, usually, because there's huge stars that sometimes looks like they're getting closer or farther, but usually things that are getting closer turn into blue shift. Things that are getting farther get into red shift. Yeah, we knew that part. Yes?
Will this telescope help us see the asteroids that may or may not be coming in 2022?
I can,
Repeat the question.
but the question was like if this telescope will help us see the asteroids that are coming our way, and hopefully the ones that are coming before 2032. If you guys don't know about it, there's an asteroid, 2014 HY or HD, I think is the name, and it is supposed to hit us, but that probability went down really, really quick.
Yeah.
So it's not an issue. One good thing about it is like we have a department that is scanning the skies all the time. We know what is out there. We know like if a spaceship's coming, we know. We have like around 95% of all those asteroids that actually can harm the planet. And we know about like 80% about the planets that are like a couple kilometers. So we do know about those asteroids. All the
Red shirt.
red shirt.
Everyone's talking about dark matter. Can Red see dark matter? How is it detected? And also, one more question. Is it true the Apollo missions that cloud is truly flying up there?
Well, I'm gonna answer the second question. First question was if with the James Webb we could see the dark matter and study it, and the other question was like if in Apollo we actually put the flag on and it was actually moving out there. And yeah, it was barely movement in the flag because there is not as much wind, although there is, and there is even earthquakes and everything in the moon too. But yeah, usually like the gravity helps with the movement, so it was pretty still. Probably it's not even there anymore because of radiation, that flag. And second question, because we don't know what exactly is dark matter, what we can do is observe how the environment around it works. You know, like if we see kind of objects moving in a weird way or faster way that they're supposed to just fly away, and it doesn't make sense that gravity is keeping in there, maybe we know like, oh, maybe we can see that there's a blob of dark matter there. Oh, maybe there's more dark matter here than there. Maybe we can see how dark matter moves around because it's pretty much everywhere. But or maybe answer questions like, is it cold or is it hot? Because we know like matter when it's cold, it doesn't move as much. So that's one thing we kind of know about dark matter. Maybe we can prove if that's true or not, because things that move too much, usually they're hot. So.
I have a question. Sorry about that. When the telescope is unfolding, is that something that you're doing with the program on the planet here, or is that something that is programmed into the telescope to do itself?
Yeah, we have to press the key
The
to send the
question?
signal. The question is like if the telescope, when it was unfolding, if it was pre-programmed and it just knew when to start doing it. No, we have people here literally sweating a lot, just pressing the key and hopefully opening. Oh my God. Yeah, there's videos of that. It's really fun. Hopefully with different key. And thank you guys.
Oh. We had a question. Oh yeah. I was like, yeah, I think so too. Uh-oh.
Okay, listen, there were several hands in the air, and I am so sorry that we did not get